Okay, so myself, I am Tahira Mazumder from IT department in AKGEC. Today I'll be talking about the topic Data Encryption Standard, DES, which comes under the subject Cryptography and Network Security under AK2 syllabus. Okay, to start with, first let me give a brief introduction about DES. What exactly DES is? It is basically a symmetric key. It is a symmetric key block cipher, and it was published in NIST, a National Institute of Standard and Technology, and it was adopted as a standard for encryption decryption in USA in 1977. So it came somewhere in 1970s. It was actually developed in 1974 jointly by IBM and US government, and the purpose of doing so is to come up with a standard means of communication for ensuring security. So this is a block diagram of DES. At DES, basically it works on block cipher. What is a block cipher? A block cipher is a cipher which works on block of data. Block means collection of bits. So for DES, the block size is 64-bit. So DES takes a 64-bit plain text and it outputs a 64-bit ciphertext. For doing so, it uses a 56-bit key. And as we know, for every encryption, we will be doing a decryption. The encryption will be done at the sender's end, and the decryption will be done at the receiver's end. So that at the sender's end, we'll be converting the plain text to the ciphertext, and the ciphertext will be communicated. It will be communicated over the network. It will be communicated over the network to the receiver. At the receiver's end, the receiver will get the ciphertext, which is a 64-bit key, and it will use this 56-bit key and generate the 64-bit plain text. This is the decryption part and this is the encryption part. So today I'll be talking about how DES works. This is the block diagram of a DES. The block diagram is, we start with 64-bit plain text. These are the phases that we'll be going through for DES. We do the initial permutation to the 64-bit plain text, followed by some rounds. In case of DES, we have 16 such rounds, followed by a final permutation. For each round, we are applying a 48-bit key to each round, which is, this 48-bit key is generated from a parent 56-bit cipher key. And we have a round key generator, which is an algorithm basically. The task of this generator is to convert the 56-bit key, which is fed for the DES, to convert this 56-bit key to 48-bit keys. Now, because we have 16 rounds, the round key generator will be generating 16 such number of 48-bit keys for each of the 16 rounds that we have. After the 16th round, we'll be doing a final permutation, and finally we'll be getting a 64-bit ciphertext. Fine. So this is the broad flow chart or broad structure of how the DES works. So I'll be talking first about what happens in the initial and the final round, what happens in the initial round and the final round. Then I'll be talking about what happens inside each round. And finally, I'll be talking about the round key generation. So the flow of the lecture will be, first we'll be talking about the permutation. Next, we'll be talking about what happens in the rounds. And next, we'll be talking about how the key is being generated. To start with, we are talking about the first step now. So in every slide, I'll be having this block diagram of the DES for us to map to which stage we are right now. So first we'll start with the initial and the final permutation. What happens in the initial permutation round and the final permutation round? First we'll talk about this, then we'll talk about the rounds, and then we'll talk about the round key generation. Now let us come to this stage, initial and final permutation. If you remember, as I told you, in case of the block diagram, the input to each block is a 64-bit plain text. So what happens is that, so what we are doing here, we are taking this entire 16 rounds, we're taking it as a black box here. Because our focus is not on the rounds now, our focus is on the permutations. So we are considering this as a black box kind of thing. The input to this round comes from the initial permutation, and the output from this round goes to the final permutation. So our focus is right now on the initial and the final permutation. So let us see what happens in the initial and final permutation. If you remember, we have 64-bit key. So this is how the keys are being aligned. First bit, second bit, third bit, 8-bit and the 64-bit input to the structure or to the circuit for performing initial permutation. Now what in case of initial permutation, what happens is that we just shuffle the positions, the inputs that are coming to some the inputs that is coming in a certain position, we shuffle their corresponding output. Like in this example, the input which is coming in the first input will be diverted to the 40th output. Fine. The one which is coming, let us say, in the second input will be diverted to the 8th output as you move on from top to bottom. So, or rather we can say, let us take some more example. The one which is at the 58th input, it will be going to which output? The first output. The one at the 64th input will be going to which output? The 64th it will be going to the 25th output. 64th input gone to the 25th output. So this is a figurative representation of how we are shuffling the inputs to the corresponding output. And if you, the corresponding tabular representation, this is the corresponding tabular representation. The tabular representation, if you see, this is how it works. If you see, we have in the first position, which input comes? The 58 input comes. So in the first position, the 58 input comes. Next, I'm just taking some examples. The rest examples are implied. Next, in the 8th position, which input comes? The one from the second. So if you just see this is the 8. This is the first position. This is the 8th position. So in the 8th position input, which input is coming? In the 8th position, the one from the second input is coming. So the one from the second input is coming. Similarly, we can say, we can take some more example. Let us say in the 40th input. 40th input, which is coming? The 1th output. So let us say this is the 40th. This is the 40th. This is the 40th position. So, right. So in the 40th output, which input is going? The 1th output. So this is the 40th position, the 40th output, and in this output position, which input is coming? The 1th. So thereby, in this structure format, we are drawing this table as we are going from top to bottom. So this tabular pattern is drawn to show how exactly we are performing the permutations to the input bit pattern, input data. Fine. Now, next is, if we are doing while going from top to bottom, or rather while encrypting, this is how we are doing. This is the permutation we are doing. Now, while decrypting, it will be in the reverse direction, because we need to get back our original bit pattern or original data. So as we are decrypting, what happens when you are going from bottom to top? If you just see in the first position, which one should go? The 40th input, because we are going from, in case of decryption, we will be going in the reverse direction. The 40th input will go to the first position. So in the first position, what comes? The 40th input comes. Similarly, let us take some more example. Let us take an example of the 40th. Then let us take the example of the second position. So in the second position, what is coming? The 8th input. So in the second position, the 8th input is coming. Similarly, the entire table is drawn. Fine. So thereby we have two tables, the initial permutation and the final permutation, let us say for this particular graph. So here what we are having is that when you are going for encryption, going from top to bottom, will be going for this table, and when you are going from bottom to top, or rather decrypting, will be going for the final permutation. Fine. Similarly, we have this figure. Similarly, we are doing some kind of permutations. So as we said, these permutations, the initial and the final permutation, they are actually straight P boxes. Straight means the number of inputs to the P box. P box stands for permutation box. So straight P box means the number of inputs to the P box and the number of outputs to the P box are same. Straight P box is something like this. If you have n inputs, then you will be having n outputs. So what the figure which we are using here, this is an example of straight P box. Because why? We are having 64 inputs, and similarly we are having 64 outputs. Only difference is that we are shuffling the position. So it's an example of a straight P box, and we don't have any other algorithms or cryptographic significance in those particular structures of initial and final permutation. In every slide, I'll be using the block diagram, the main block diagram of the DS, so that we can relate to which position we are exactly right now. So I've talked about the first topic, what happens in these permutations, how exactly do we shuffle it. Next, we will be talking on the rounds. As if you remember, we said that we'll be talking about three things: the permutation, the rounds, and the round key, and the key generation. So now the focus is on the rounds. Now, what are rounds? As I told you, it uses 16 rounds. Fine. Now, our focus is on each round. What happens in each round? So, this particular figure is for each round. Now, this round has, if you remember, we have 64-bit data that is coming to the input of the block cipher. So, the 64-bit data will be divided into two parts, 32-bit, 32-bit. So, this is the left part and the right part. So, inside each round, what happens? We have a function. Now, what does it do? Let me put it like this. Inside each round, we have the left half XORed with what? With the output of a function. And what is this function? This is a function which takes two input, the right input and the key. The output of the function is XORed with the left half, and after you get the final output of this XOR gate, it is now swapped with the right half and the left half. And finally, you are getting a new 64-bit pattern after one round. Now, if you see this, after one round, if you observe this, we are basically working on the left half. On the left half, we are XORing. The left half is XORed with the output of a function. So basically, we are making changes on the left half. The left half is being swapped to the right half. If you see, the right half is not being touched. In the right half, we are not making any changes. So that is the reason we are swapping the left half and the right half. Why so? Because once we go to the, if this is the rith round, let me put it like this. This is round number, let us say round number I minus 1. So when you go to round number I, in this case, we'll start with this left half and we'll be performing this XOR and the entire operation with this left half. And the right half will remain untouched. And if you remember, as I said, what is this left half? The left half is the right half of the previous round. So that means in each round, as we are taking initially, what we are doing, we are taking the left half, we are XORing we are performing some operations on the left half, and we are coming up with a new bit pattern for the left half, but the right half is unchanged. So after each round, we are swapping the left and the right. Why? Because the right half, which was not being touched upon, will now be worked upon, and it will be converted to a new bit pattern. So this is what happens inside each round. So if you summarize, we are saying inside each round, what happens? We have an XOR gate, we have a function, and we have the swapper. We all know what an XOR gate is. That's very trivial. We know how to swap to bit pattern, but what we don't know is what exactly the function is. So the next focus is, what is this function? To understand what happens in this function, how does this function work on this two inputs? So now our aim is to understand what happens in this function. So right now, again, I've included both the parent block diagram so that we can map to where exactly we are. We've taken the permutations. We are talking about the rounds. We have said that inside each round, this is what happens, and we have said that inside each round there's a function, and now we are trying to understand what exactly happens inside the function. Now, inside the function, let us say this is an example of a function. So this is a function, this one, right? This entire box is now expanded. This fx is this f of ri minus 1 and ki is this one, fine. Now what happens is that, what is input? If you look at this function, what is the input to this function? The input to this function is basically a 32-bit pattern. Why? Because the input is coming from the right half of the 64-bit. So the input is a 32-bit pattern. Now this function, what it has, inside this function we have an expansion p box. Expansion, what it does, it has less number of inputs, it expands the number of inputs. So what does this p box do? It takes this input 32-bit pattern and it outputs 48-bit pattern. After that, what it does, it XORs. XORs with what? XORs with the key. What is the key? If you remember, each key is a 48-bit. Each key is a 48-bit. So every round is having a key input of 48-bit. So the key input which is coming for each round, it is 48-bit. So the 32-bit is expanded to 48-bit, XORed with the key which is a 48-bit. Finally, we have an output which is a 48-bit. Then what we do, we are taking an S box, substitution box, which converts the 48-bit to the 32-bit. And then finally, we have a straight P box, that means we do some permutations. And again, we may come up with a new bit pattern of 32-bit. And finally, we have our output. And this output is what comes out from the output of the function. And this is what goes here. and the entire figure is expansion of this particular figure. Okay. Now, so we know, we have understood, gone to the body of the function. This we know XOR gate. What we don't know is expansion P box, the S box, and the straight P box. So now we'll be talking about expansion P box, the S box, and the straight P box. So let us come to the expansion P box. This is your expansion P box. Again, I'm saying we are in the 48. We are talking about a 48-bit, 64-bit block cipher, which is DS. We are talking about round. Each round has functions, and in each function we are talking about F. This is the function inside each round, and each round has an expansion P box which converts a 32-bit to 48-bit. Now, what happens is that this is a 32-bit input which is converted to 48-bit output. What happens? This 32-bit input, we are dividing it into 1, 2, 3, 4, 5, 6, 7, 8 equal parts. So if you divide 32 into 8 equal parts, we are having 4-bit for each part. So that is what you're saying, 4-bit for each part. So we are having 8 number of parts with 4-bit input for each part. Then after that, what you're doing, we are mapping this 4-bit, we are converting this 4-bit input to a 6-bit input. Fine. And how many such inputs do we have? How many such parts we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have got 8 such parts. So 6-bit, we are converting a 4-bit to a 6-bit input. So ultimately, the total number of bit patterns we are having is 6 into 8, that is 48-bit. We'll be ending up with 48-bit patterns. So now, how exactly do we convert this 4-bit to a 6-bit? Now, if you look at it, so each 6-bit, the middle 4 bits of the 6-bit pattern straightaway comes from the 4-bit input. Fine. Now, the middle 4 bits. Now, what about the ends? If you just let me come to this example, the middle 4 bits are coming straight away from the input. The first bit and the 6th bit, the first bit and the 6th bit rather, will be coming from the previous 4 bits, last bit is replicated here, and here the next 4-bit first bit is replicated here. This is how we convert a 4-bit to a 6-bit. I'm again explaining. We have a 4-bit input to the expansion P box, 32-bit broken up into 8 parts, 4-bit. This 32-bit is broken up into 8 parts. So we have 4-bit, and each 4-bit we are trying to convert it into 6-bit. Fine. And how do we convert? The 4-bit, we are mapping them as it is in the middle 4 positions. The remaining 2 extremes, from the leftmost, the left 4-bit slot, we are putting the last bit of the left 4-bit as the first position, and the first bit of the next 4-bit in the last position. This way, we are creating a 6-bit pattern, a 4-bit converted to a 6-bit, 4-bit converted to a 6-bit. Now, let me take a tabular form of this figure to make it more obvious. Now, if you let us take a tabular form, let us come with the first one. And okay, one more thing that I want to say is that, what about the last and the first bit pattern? In case of the first bit pattern, the 5th bit comes from the first bit of the next 4-bit pattern. But whatever the first bit, it will be doing a wraparound. From the 32th bit, it will come. Fine. Similarly here, in the last pattern, in this case, the first bit comes from the previous bit pattern, the last bit of the previous bit pattern, but whatever the last bit, it will be coming from the first bit. So there is a wraparound for the first lot and the last lot. Now if you are trying it in a tabular pattern, this is how it looks. For this one, if you see, for this one, this is the first bit, the second bit, the third bit, the 4th bit. What about this? This is the 32th bit coming from this position. What about this? This is the 5th bit. This is for the first 6 bits. Now let us come to the next 6 bit. The next 6-bit pattern, if you look at it, this is what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. We go till 32 because you have 32-bit input. Now, let us come to the next bit pattern. How are you getting the next 6-bit pattern? This is the first 6-bit pattern, the first 6-bit pattern. The next 6-bit pattern, how are you getting? The middle 4 bits as it is, 5, 6, 7, we are just transferring it from the input. Whatever the extremes, the leftmost bit will be the 4th bit, Whatever the rightmost bit, will be the 9th bit. You see, this is how it happens. Similarly, we'll be doing for the remaining slot, and this we are coming up with the resulting table. The resulting table, this entire number of total number of bit, total number we have right now 48 bits. We have total 48 bit output, if you can calculate it right now. This is your 4-bit, so this is for the first 6-bit, the second 6-bit, the third 6-bit, and so on, and we'll be having it for how many such 6-bit? The first, the second, the third, the fourth, the fifth, the sixth, the seventh, and the 8th. So 8 number of 6-bit patterns you are getting, and so 8 into 6 is 48. So you are getting ultimately what we are getting? We are getting a 48-bit output. So this is how I just explained how exactly we are converting a 32-bit pattern to a 48-bit output. Now this 48-bit output is XORed with a key which is a 48-bit. I'll come to the key generation later on. This is XORed. After XORing, we are getting an output which is 48-bit. I'm not going into the detail of XOR. We all know what XOR is. Fine, that is very trivial. Now we'll come to S-box. We know how expansion P-box works. Let us come to S-box. Now S-box is a substitution box. If you remember the concept of substitution box, I'll just brush up from a little bit about it. So this we are having how many such S-box? 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 8 such S-box. How many inputs? 48 inputs. 48-bit input. So 48-bit input is fed to 8-bit S-box, right? So that means in each S-box, how many such inputs will you have? 48 by 8, that is 6-bit. So each S-box, in each S-box, they will take an input of 6-bit pattern. Each S-box will get 6-bit in pattern. And this S-box together will convert the 48-bit to a 32-bit pattern. So let me explain how exactly it is converted. So now we are coming to, I've explained, we are talking about the function. Right now the progress is function. What is this function? This function is inside each round. Fine. So we are comparing to a function. In the function, we have already explained P-box. We are now starting with S-box. As I said, we'll be having 6 S-boxes. 1, 2, 3, 4, 5, 6, sorry, 7, 8 S-boxes. 8 S-boxes as I told you, because, and since we are having 8 S-boxes, and we have 48-bit key, 48-bit data. So if you are dividing it, we are having 6-bit for each S-box. So each S-box has got 6-bit input, if you see. Each S-box is taking 6-bit input. So this is how we are saying. So we have 8 number of S-boxes with 6-bit input. Fine. S-box 1, S-box 2, S-box 8. Fine. Now what does this S-box do? It substitutes 6-bit data by a corresponding 4-bit data. Each S-box takes a 6-bit input and substitutes by a corresponding 4-bit data. So that means, and how many such S-box we are having? We are having 8 such S-box. So each S-box is giving you 4-bit output. So how many ultimate output will be 4? Each S-box giving 4-bit output. How many such S-box? 8 such S-box. So ultimately 4 into 8, we are getting 32-bit pattern. So you are giving a 42-bit input, and ultimately we are getting a 32-bit output. This is how it works. Now the next point is what exactly happens inside the S-box. What is the concept of the S-box? Fine. So now so right now we have talked about P-box. Now we have talked about using 8 number of S-box, which takes each S-box taking 6-bit data and giving as output 4-bit data. Now we'll come to each S-box. What exactly does each S-box do to convert a 6-bit input to a 4-bit output? Let us come to that. Fine. Now, before I take up that particular method, how S-box is converting a 6-bit input to a 4-bit output, let us just brush up a little bit about S-box concept. S-box is also called a substitution box. It is basically, we can also say that it is a miniature substitution cipher. And basically an S-box is an M by N matrix, we can say, or a substitution unit, where M and N are not necessarily equal. They may be equal or they may be unequal. So let us take an example. This is an example of an S-box. So if you look at this, we have a substitution box for encryption. It's something like this. Is a table that will be pre-decided upon. And let us say, for example, you want to substitute how to substitute 000 or let us say 0, 1, 0, or let us say 1, 0, 1 or 1, 1, 1. What will be the corresponding substitution of this bit pattern? How do you substitute this bit pattern by a new bit pattern? Or rather, when you are encrypting it, we are converting a data pattern to another data pattern so that a third person cannot read those bit pattern. So 0, 0, for 0, 0, you go to the matrix and find out what is there in 0, 0. So you have 0, 1, 1. So that is how we are substituting 0, 0, 0 with 0, 1, 1. What about, let us say 0, 1, 0. So 0, 1, 0, this is the entry. So it will be substituted by 1, 1, 1, 0, 1, 1, 0, 1. So that will be 0, 1, 0. 1, 1, 1, 1, it is 1, 1, 0. This is what you do during the encryption part. Now in the decryption part, it will be just the reverse. What we have as values for the matrix, they will become the addresses here, and what we have as the addresses or the indices of the matrix, they will become the values. We'll check it out. Like for example, for 0, 0, what was the index? It is 1, 0, 0, right? So what we'll do for 0, 0, we're going the opposite way. For 0, 0, the value will be 1, 0, 0. Similarly, let us say for 1, 0, 0. For 1, 0, 0, what is the addressing index? 0, 1, 1. So 1, 0, 0. 1, 0, 0. This is the entry. So you'll have 0, 1, 1. So we're just doing that. We are just shuffling the values with the indices to get a new substitution table for decryption. So once we get this table, how do we decrypt? Now, for example, we want to do it for 0, 1, 1. We are going the opposite way. For 0, 1, 1, what will be the corresponding mapping pattern? So let us go to the table 0, 1, 1. The corresponding mapping pattern is 0, 0, 0. And if you check, that is what actually it is. I'll just take one more example. Let us say for 1, 1, 1. For 1, 1, 1, what is the value? 1, 1, 1, 1, 1, 1. The value is 0, 1, 0, 0, 1, 0. Sorry, it is 0, 1, 0. And if you just see, that is what we are having. For 1, 1, 1, it is 0, 1, 0. So in case of encryption, if you are mapping, if you are mapping from 0, 0 to 0, 1, 1 using the substitution box, we are substituting. There's no logic. We're just substituting a bit pattern by another bit pattern, but we need to have two S boxes, one for encryption and one for decryption. So in the encryption part, we are replicating 0, 0 by 0, 1, 1. So in the decryption part, we are just doing the reverse. 0, 1, 1 will be replicated by 0, 0, 0. So you are going back to our original pattern. How we are doing that? By using the substitution table or the substitution box. And in substitution box, we could just follow some predefined rule and we substitute a bit pattern by a new bit pattern. So that particular logic will be using in the S boxes. What I explained, the same logic is used in the S boxes. If you remember, each S box has got 6-bit input and it gives a 4-bit output. Each S box takes a 6-bit input and gives a 4-bit output. So how does it work? So if you see, this S box follows a predetermined rule. The rule is predetermined, the tabular pattern is predetermined, and the rule is based on a 4-row 16-column table. It is a matrix of size 4 by 16. Fine. Now what we do is that the combination of the first bit and the 6th bit, the first bit and the 6th bit, the first bit and the 6th bit. Fine. We just say this is your first bit, this is your 6th bit. They will be giving you deciding which row to access. Like if you have 2-bit pattern, now because it is 2-bit, it can be 0, 0, 0, 0, 1, 1, 0, 1, 1. So if it is 0, 0, you'll go to the first row. If it is 0, 1, you'll go to the second row, and so on. So the first bit and the 6th bit gives you the row address, which row you want to go. And remaining the 2nd, 3rd, 4th, 5th bit, that means you're getting 4-bit pattern, right? 4-bit pattern, how many such combinations you can have? 2 to the power 4, 16. 2 to the power 4 is 16. And if you number from 0, you'll go from 0 to 15. 16, if you number it from 0 to 15. So you'll have, using the 4-bit pattern, you'll be having 16 such addresses. Fine. So this is how you are having 4 rows and 16 columns. And using the 6-bit address, you are converting it, you are zeroing down on a certain location, and that location will be having a 4-bit pattern. It will be having a 4-bit pattern. So this is how we are converting. It will be, this pattern will be pre-decided, like the table which I already explained. And this is how we convert a 6-bit to a 4-bit and this is for each S box. Let us say this is for S box 1. Similarly, we will have S box 2, S box 3, and so on. This is and the figure which I just right now explained, if you remember, this is the figure. Fine. So we have this S box, and if you explain it, this is the tabular pattern of that S box, the tabular pattern. If you see, we have 4 rows. We have 4 rows, 16 columns. You have 4 rows and 16 columns, and inside this is the values that are pre-decided, and we substituted by this values, and you'll be having such 16 number of S box. You'll be having how many such tables? We have 1, 2, 3, 4, 5, 8 S boxes. So you'll be having 8 number of such tables. So we have already explained the expansion P box, the S boxes. Now the next topic is straight P box. What exactly a straight P box does? It just does the permutation, straight permutation. Straight permutation means number of input and the number of output is same. 32-bit input giving a 32-bit output, and this is the permutation pattern. If you see 1, 2, 3, 4, 5, 6, 7, 8. You have got 8 columns. 1, 2, 3, 4. 4 rows. So total number of entries you have 4 into 8 is 32. So this is a 32-bit pattern of permutating. How do you permutate? The permutation is in the first position you bring the 16th bit. In the second position, you bring the 7th bit. In the third position, you bring the 20th bit, and so on. This is how you do permutation, and as you're going from top to bottom, or otherwise you're encrypting. And if you're decrypting, you'll just reverse it, as I showed in the first slide. So this is how the straight P box works. So I have explained how exactly the function is. Inside the function, we have talked about how expansion P box works. We have talked about S boxes. We've talked about straight P boxes. So next is, so we have talked about permutations, we have talked about what happens in each round, and we have 16 such rounds. And finally, the next topic is how to generate the key. Now, this is just a brief overview of how the pattern it works. 64-bit pattern. This is your first round, the second round, and so on till the 16th round. Each round, this is your function, and right now we talked about how the function works. If you go from this in this direction during encryption, during decryption, you'll be going in the reverse direction, and you'll get a plain text starting with a 64-bit ciphertext. So this is the last topic. The last topic is, if you remember, we have talked about permutation, or we have talked about rounds, what happens inside each round. We have so many components inside each round, how it works. The last topic is the key generation. What does the key generation do? It converts a 56-bit key to a 48-bit key. How does it convert? Let me just explain that figure. You have a 56-bit key. This is a 56-bit key. Now we have for parity purpose, we all have learned in networking, we make it 64. The key is basically a 64-bit key with parity bits included. We remove the parity and come down to a 56-bit key. So our original key is a 56-bit key where we are dropping the parity bits, fine. And once we are coming to a 56-bit key, we are again dividing this into 28-bit key, 2 halves. 28-bit key, 28-bit key. Now what we do is that if you look at the key generation part, each 28-bit key is shift lefted. It is being shifted left, and then after left shifting, we are getting a new 28-bit key. So we are getting a 46-bit bit pattern. So 28 plus 28 is 56-bit input. We are getting 28-bit is coming, 28-bit is coming. So how many bit is fed to this compression P box? 56-bit. What does this P box do? It converts the 56-bit to a 48-bit. So it is again a compression P box which takes 56-bit input and gives a 48-bit output. This is the first round. Second round, again we do the left shift. After left shift, we are getting a new 56-bit pattern. We apply a P box, compression P box, which converts a 56-bit key to a 48-bit key, and this entire process repeats. For how many times? Because we need 16 such keys, it will be repeating for 16 number of rounds. Now the next point to be understood is that left shift. How many times will you left shift? Now that depends. When you're in the first round, the second round, the 9th and the 16th round, we'll be left shifting it by 1 bit. And for all other rounds, you'll be left shifting it by 2 bits. That is what you need to remember. That means in the first round, when you are shifting the bit pattern, you'll be shifting it by 2 bits. In the second round, you'll be again shifting it by 2 bits. In the 9th and 16th, again by 2 bits. For all other rounds, you are shifting it by 1 bit. this is how the compression, this is your compression table. What is the compression table? The compression, if you remember, the compression table is converting, taking a 56-bit key and converting it to taking a 56-bit key, converting it to a 48-bit key. This is your entry. See, we have 1, 2, 3, 4, 5, 6, 7, 8 columns. 1, 2, 3, 4, 5, 6. 6 is 48. So we have 6 rows into 8 columns. We have 48 values, 48 values. So this is the 48 bit pattern that we get, and the possible values out of this, see what happens is that the input is a 56 bit, the output is 48 bit. So 56, so what happens is that out of the 56 values, we'll be taking up only 48. Some values might be missing. Like in this example, if you see 1, 2, I guess the third value is missing. Third, fourth, some values might be missing. If you check it out, fourth, is it there? I guess fourth is there, not there. Fourth value is missing. Fourth is missing. Similarly, some values will be missing. So total missing values will be 56 minus 48. So 8 values will be chopped off. When we are converting 56, 8 values will be chopped off. How? When we are converting, our input is 56 and we are converting it to 48. So when you are converting a 56 input to a 48-bit input, 8 values will be chopped off, and this is the values which will be taken care of. The remaining missing values are the 8 values which are chopped off, and this is what a compression P-box does. This is what a compression P-box does. So we have talked about the key generation, we have talked about the permutation, we have talked about the rounds, we have talked about how the round key generation works, how it converts a 56-bit key to a 48-bit key. To convert it, you have this table of converting a 56-bit key to a 48-bit key. We are using a compression P-box, and we are having a multiple rounds. In each round, we are shifting the data as getting a new data input for the compression P-box, and similarly, we are having 16 such rounds. So this is a final summary. We have, as I said, I have taken the bit pattern, I have shown how the permutation happens, I have talked about rounds, what happens inside each round. You have the left half, you have the right half. The right half is XORed, right? In the right half, we are applying a function. The function is XORed with the left half, and so on. The entire function is being, I have explained what happens inside the function. We have P boxes, we have S boxes, how it converts the data, a bit pattern, a 46-bit bit pattern to 32, and so on. So many things we have already explained. We have explained each round. We have talked about how keys are generated, how it converts a 56-bit key to a 48-bit key, the entire. So to summarize, this is what we need to learn: how permutation is happening, how rounds, what happens inside each round, what happens inside key generation. And I have talked about all these 3 points, and this 3 in totality makes up your DES, data encryption standard, the algorithm for DES. So in the next class, I'll talk about something related to cryptography related to DES. Maybe I'll come up with other types of DES and so on. So that much for now. Thank you.